All right, I hope that in the last video you came to the place where you believe me that a Taylor polynomial of degree 6, of order 6, that approximates cosine of x at places where x is very close to 0, is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th 6 factorial. If you needed more terms, you could keep going. You probably catch on to the pattern. So we found that one by hand by actually going through and finding the derivatives, and we said, okay, it wasn't so bad because every other derivative is going to be 0. You might find that you'd like to know this Taylor polynomial, this Taylor series approximation by heart. But know that on the AP test, you could, if you had to, pull it out, as long as you remember this. Let's see if I can scroll here. This definition for a Taylor series, f of 0, if at centered around x equals 0. F of 0 plus f prime of 0 times x plus f double prime of 0 times x squared all over 2 factorial. And then we noted these patterns that can help us. This is second derivative of 2 factorial and x to the second. This is the nth derivative, n factorial, and x to the n. And I hope that in class today you did that next problem, which is to make the 7th order Taylor polynomial for sine of x. And you'll notice that the sine Taylor polynomial and the cosine Taylor polynomial, they're each missing like half of their terms, right? Because every other derivative happens to be 0. But for sine, it's the other derivatives, the ones that weren't missing for the cosine polynomial. All right, so just notice that this was our answer for construct the 6th order Taylor polynomial for cosine of x at x equals 0. Notice here I've asked you this next question. Find the 4th order Taylor polynomial that approximates y equals cosine of 2x near x equals 0. So I'm looking for a polynomial of the same center as the one I wrote here. The one I need now is degree 4. I have degree 6, so it's like I have too much. But I'm supposed to have an approximation of cosine of 2x. So notice that once you have an approximation for one Taylor polynomial, and for a Taylor approximation for one function, you can do what we did back in 9.1 and just transform that. So I could write that cosine of 2x would be approximately equal to, and I'm going to write the same expression. I'm not going to use this term because I've only been asked to give the 4th order, and this goes up to the 6th order. 4th order means it came from using the 4th derivative. And everywhere I see x in this polynomial, I'm going to replace it with 2x. And I could choose to simplify or not. So this is going to be 1 minus, instead of x squared, I'm going to have 2x squared over 2 factorial plus 2x to the 4th over 4 factorial. If for some reason you got totally stuck, you could go back to that definition for a Taylor polynomial, find all those derivatives, and create this polynomial. But notice also, if you have something that's related, in this case you had a Taylor polynomial that approximated the cosine function, you could perform any kind of algebraic transformation that we talked about in the last section to transform it into a new polynomial. Notice you absolutely must use approximately equals to here. If you wrote cosine of 2x equaled 1 minus 2x squared over 2 factorial plus 2x to the 4th over 4 factorial, you would not get full credit. But if you then wrote plus dot 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 to indicate that this Taylor polynomial went on forever, which would make it an infinite Taylor series, that is a true statement. The only thing that makes it an approximation instead of an exact value is that we're chopping it off after some number of terms, just for our convenience. Okay. Okay, so remember back in chapter 4, we could make a tangent line approximation to a function at any x value we cared about, as long as we knew the function value and its derivative at that x value. So the same is true for a Taylor polynomial. All the approximations we've made so far, we wanted them to be really good fits for our function at the place where x equals 0. But what if I care about having a really good fit somewhere else? I can do the same thing, and really what occurs is simply a transformation, a horizontal shift. Remember that if I replace x with x minus a everywhere in a function, that takes my exact same function and shifts it a spaces to the right. So that's what this does, is I can write all that same Taylor polynomial stuff, and if I want to have it match up at a certain x value, which I'll just call for a for convenience, all I have to do is replace all of the x's with x minus a's. So same process to go. What if I want to find the Taylor series generated by e to the x, and I wanted my approximation to be a really good fit near the place where x equals 2 instead of near the place where x equals 0. So I'm going to leave this box right here that's going to help us out. So this says Taylor series. It doesn't tell me of what order or how many terms. So that tells me I have to show an infinite series, including, it would be appropriate in this case to include a general term. So I'm going to use this pattern. I'm going to use this expression that's up here. I'm going to see if I catch on to the pattern. So in this case, a equals 2. So I'm going to need f of a. So I'm going to write e to the x near places where x equals 2 is approximately equal to, actually if I end up making this infinite, then I'm going to be able to go back and change that to an exactly equal to. But f of a and f of x is e to the x, so this is going to be e to the 2, so e squared plus f prime of x, f prime of x, God bless e to the x, right? He's his own derivative, so f prime of x is also going to be e to the x, and f double prime of x is also going to be e to the x, and f double prime, f triple prime, f fourth prime, they're all going to be e to the x. So this is going to be f prime of a, which is also e to the 2 times x minus 2. To the first, if you want to put that, but that's not required. Plus the second derivative of f is also this e to the x, and I'm going to evaluate that at a to get e to the second times x minus, oops, I know a is 2, squared. That gets divided by 2 factorial, plus, this is going to be e squared again, x minus 2 cubed all over 3 factorial plus dot dot dot. So now that I've got that idea, how would I write that pattern? I would probably write out 3 terms and the general term. So even though this is totally correct, I have written it in a way that I don't have any more room, so I'm going to erase this so I can write sort of a final answer. So e to the x near x equals 2 is exactly equal to e squared plus e squared times x minus 2 plus e squared times x minus 2 squared over 2 factorial plus dot dot dot. Well, this was the 0 term, the first term. The second term, I'm going to call this, so that gives me, like, if I wanted to think, what would the nth term look like? Well, it's going to be e to the n, x, no, bah, 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 bah. That was always e squared, because that was supposed to be the nth derivative evaluated at x equals 2. And the nth derivative for this function, because it's special and awesome, is always e to the x, so evaluate that at a, and we always get 2, which is e squared, times x minus 2 to the n over n factorial. plus dot dot dot. If I'm going to write that general term and use the plus sign with the dot 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 to show that I could continue this series forever, then that's actually exactly equal to e to the x, near where x equals 2. Your life on the AP test will be easier if you remember some of these Taylor series by heart. This one I expect you already know by heart, and that's just the geometric series with r equal to x. This one, sine, cosine, sine of x, cosine of x, and e to the x, those are the ones you really are going to want to know by heart. They will, you could always stop and figure them out on the AP test, but it's not uncommon for them to say, write the first 4 terms of the Taylor polynomial approximation for e to the x, and then in the next step use it to do some other thing. So if you know these, well, this is not an option, you have to know that one by heart, but if you know these 3 by heart, you'll find that your work on the AP test goes faster.